Imagine sinking through the ocean, past the playful shimmer of the surface, past the blue that slowly deepens into navy, then into something closer to ink. At first, light just feels tired, like it forgot its coffee. Then it vanishes entirely. Not dim, not twilight. Gone. At this depth, the sun is not late. It is irrelevant. You are now in a place where day and night lost their meaning millions of years ago, where no sunrise has ever broken the horizon, and where the idea of a shadow would sound like science fiction. This is the deep sea, and it is not empty. That fact alone should already make your brain itch a little. Because almost everything we know about life on Earth starts with a very simple rule. Energy comes from the sun. Plants catch sunlight. Animals eat plants. Other animals eat those animals. And everyone agrees to pretend this is normal. Remove the sun from that equation, and the entire system is supposed to collapse like a poorly assembled bookshelf. No light means no plants. No plants means no food. No food means no life. End of story. Except the deep sea did not get that memo. If this slow exploration of how the deep sea builds entire ecosystems without light helps you unwind tonight, please like the video, subscribe to the Deep Sea Documentary channel, and leave a comment sharing when and where you're listening, so this calm science can reach more people who drift off to sleep beneath the ocean. Down here, under crushing pressure that would turn a human into an expensive pancake, life is not only surviving, it is thriving. There are dense communities packed together, organisms stacked on organisms, yet entire neighborhoods of creatures interacting, competing, reproducing, and generally doing all the things ecosystems do. If ecosystems were supposed to need sunlight to function, then this place is either breaking the rules or quietly rewriting them. And the first thing that hits you, even before the biology, is the atmosphere. It is silent in a way that feels heavy. Water absorbs sound differently down here, and without waves, wind, or weather, the ocean feels still. But that stillness is deceptive. Because in the darkness, things are moving, slowly, deliberately, with adaptations refined over unimaginably long periods of time. This is not a wasteland. It is a city at night, where everyone forgot to install streetlights. The deep sea covers more of our planet than all forests, deserts, and grasslands combined, yet it remains one of the least explored environments on Earth. We know the surface of Mars better than we know much of this realm, which is humbling and slightly embarrassing. Somewhere out there is a jellyfish we have never seen, judging us quietly. And within this massive, dark expanse, pockets of life cluster together in ways that challenge our assumptions about what ecosystems even are. What makes this so unsettling and so fascinating is that energy still has to come from somewhere. Biology cannot run on good vibes alone. Cells need fuel, metabolism needs chemistry, growth needs resources. The laws of physics did not politely turn themselves off just because sunlight could not reach the sea floor. So the question becomes unavoidable. If energy is not raining down from above, where is it coming from? Standing at the edge of this question feels like standing at the edge of a mystery novel where the detective realizes the crime scene makes no sense. The suspects do not fit. The timeline is wrong. The obvious explanation is missing. And yet the evidence of life is everywhere. Worms the size of baseball bats. Crustaceans swarming like underwater insects. Fish hovering in slow motion, conserving every bit of energy like misers guarding gold. And unlike surface ecosystems, these communities do not spread evenly across the landscape. They cluster. Life gathers in hotspots, leaving vast stretches of seafloor sparsely populated or nearly empty. It is as if the deep sea itself has oases, places where the rules bend just enough to allow complexity to bloom. If the rest of the deep ocean is a desert, yet these places are glowing cities powered by something other than sunlight. There is also something deeply unsettling about ecosystems that exist entirely beyond our senses. You could stand on a boat directly above one of these communities and have absolutely no idea it was there. No color change, no smell, no movement on the surface. An entire functioning world hidden under kilometers of water, going about its business without the slightest concern for whether humans ever notice it, which, frankly, feels like a power move. This chapter is not about answers yet. It is about setting the stage, about letting the mystery breathe. Because before we explain how the deep sea builds ecosystems without light, it is worth sitting with the sheer audacity of the idea. Life did not just adapt to darkness, it embraced it. And it found ways to turn absence into opportunity, chemistry into currency, and hostile conditions into home. The deep sea is not a backup version of life on Earth. It is not a pale imitation waiting for sunlight to return. It is a parallel solution to the same problem every living thing faces: how to stay alive in a universe that does not care. And as we descend deeper into this story, we will see that when the sun disappears, life does not give up. It gets creative. To understand why the deep sea is such a rebellious overachiever, we first need to acknowledge just how powerful sunlight normally is. On the surface of Earth, sunlight is not just important. It is the head of the household. It pays the bills, sets the rules, and decides who gets to exist in the first place. In nearly every food chain you have ever heard of, starts with something green pointing its face toward the sky and soaking up photons, like it is charging a biological battery. Photosynthesis is the quiet miracle running the planet. Plants, algae, and microscopic organisms capture energy from sunlight and use it to build sugars, turning light into something chewable. From there, energy flows outward. Herbivores eat the plants. Carnivores eat the herbivores. Omnivores eat everyone and call it balance. Even creatures that never touch a leaf still depend on sunlight indirectly, because their food ate something that photosynthesized. It is one long, sun-powered game of telephone. This is why deserts bloom when it rains and collapse when the sun is too intense. It is why forests grow toward gaps in the canopy. And it is why coral reefs live only in shallow, clear water. Sunlight sets the limits. It decides where ecosystems can be dense and complex, and where life must scrape by on crumbs. Remove sunlight, and the entire structure above it is supposed to crumble. In most places on Earth, that is exactly what happens. Go underground, and life thins out. Go into caves, and ecosystems simplify. Go deep into the ocean, and for a long time, scientists assumed the same pattern held true. Less light meant less life. Eventually, no light meant no life. It seemed logical, tidy, and very wrong. The deep sea begins where sunlight officially gives up, not fades, not weakens. It simply stops. And for a while, biology follows the expected script. As you descend, food becomes scarce. Animals become smaller, slower, and more cautious. Every calorie matters. Energy is treated like a precious family heirloom passed down carefully and never wasted. If the deep sea were only this, it would still be fascinating, but it would not be shocking. The shock comes from what should not be there at all, because hidden within this sunless world are places where life does not merely survive, but explodes into abundance. Dense clusters of organisms appear where none should exist, supported by energy sources that have nothing to do with light. These ecosystems are not borrowing leftovers from the surface. They are not scraping by on falling debris. They are running their own independent economy, completely detached from the solar system's main power supply. This is where the rug gets pulled out from under our assumptions. For centuries, sunlight was treated as a universal requirement for complex life. Well, it made sense. Light is easy to access. It is abundant. It rains down constantly. Why would life bother finding another way? The deep sea answers that question bluntly. Because it can. Life does not care about convenience. It cares about opportunity. And when an opportunity exists, even in the most hostile environment imaginable, evolution will eventually knock on the door. What makes this realization so profound is that it forces us to redefine what an ecosystem actually needs. Instead of light, the true requirement is energy that can be harnessed and transformed. Sunlight is simply the most obvious option on the surface. It is not the only one. It is not even necessarily the best one in all circumstances. It just happens to be the one we are most familiar with, which made us a little arrogant. The deep sea does not reject sunlight out of spite. It simply never had access to it. And rather than surrendering, life down there found a way to build systems that operate on entirely different rules. These systems still have producers, consumers, and interactions just as complex as anything in a forest or reef. They just do not bother looking up. There is something almost philosophical about this. On the surface, life organizes itself around a star. In the deep sea, life organizes itself around the planet itself. The energy comes from Earth's own processes, from the restless activity beneath the crust, from chemistry instead of photons. It is a reminder that our planet is not just a passive stage for life, but an active participant in it. By the end of this chapter, one idea should feel very clear. Sunlight is powerful, but it is not absolute. It is a boss, yes, but not a dictator. The deep sea found a loophole in the most fundamental rule we thought governed life. And once it slipped through, it built entire ecosystems without asking permission. And that realization changes how we understand life on Earth, and maybe life everywhere else too. If the deep sea were a quiet, frozen wasteland, this story would end quickly. But the seafloor is not asleep. It is cracked, restless, and occasionally violent, in a way that does not involve explosions so much as relentless pressure and heat. Hydrothermal vents are born from this restlessness, and they are the reason the deep ocean has its own version of power plants. Picture the Earth's crust down there, pulled apart along massive seams where tectonic plates slowly drift away from each other. As seawater seeps into these fractures, sinking deep below the ocean floor, as it descends, it encounters hot rock heated by magma below. The water does not politely warm up. It superheats, reaching temperatures that would flash boil it instantly at the surface. Down here, crushing pressure keeps it liquid, like a very angry tea kettle that cannot whistle. While trapped underground, this water dissolves minerals from the surrounding rock. Metals, sulfur compounds, and other chemicals are stripped out and loaded into the fluid like cargo. When the superheated water finally finds a path back to the seafloor, it erupts out of vents, blasting into near-freezing seawater. The result is a dramatic plume that looks like smoke rising from a chimney, which is why some vents are nicknamed black smokers. They are not on fire. They just look like they are plotting something. These vents are extreme in every possible way. The temperature difference between vent fluid and surrounding water can be hundreds of degrees. The chemistry is toxic by surface standards. The environment is unstable, dynamic, and hostile. If you were designing a place for life to flourish, this would not make the top 10 or the top 1,000. And yet, life gathers here with enthusiasm. What makes hydrothermal vents so special is not just their heat, but the chemical energy they release. The vent fluids are rich in compounds that, while poisonous to many organisms, are packed with potential energy. In the same way sunlight carries energy that plants can capture, these chemicals carry energy that certain organisms can exploit. The vent does not shine, it feeds. At first glance, whilst the seafloor around a vent looks barren, then suddenly crowded, dense clusters of organisms surround the openings, forming thick biological rings that thin out as you move away. It is as if life is hugging the vent, crowding as close as possible without getting cooked. And in a way, that is exactly what is happening. Hydrothermal vents create sharp gradients. Temperature drops rapidly with distance. Chemical concentrations change over just a few meters. These gradients carve the environment into invisible zones, each suitable for different kinds of life. It is not a uniform habitat. It is a patchwork of micro-worlds stitched together by heat and chemistry. Another remarkable aspect of vents is their unpredictability. They can appear suddenly and vanish just as abruptly when geological activity shifts. A vent may roar with activity for decades, then fall silent as pathways clog or plates move. This makes vent ecosystems both vibrant and fragile. Life here must grow quickly, reproduce efficiently, and be ready to move on when the power shuts off. Permanence is not guaranteed. The physical structures formed by vents also matter. As hot fluids cool, minerals precipitate out, building towering chimneys that can reach several stories tall. These structures reshape the seafloor, creating nooks, surfaces, and sheltered spaces that organisms can cling to. The geology itself becomes habitat, turning raw earth processes into architecture for life. What is especially striking is how sharply these ecosystems contrast with the surrounding deep sea. Step away from a vent field, and the abundance drops off dramatically. Food becomes scarce again, and life spreads thin. The vent is not just a source of energy, it is a beacon in the darkness, concentrating life into places where the planet is actively doing chemistry. Hydrothermal vents force us to confront an uncomfortable truth. Habitability is not about comfort. It is about usable energy. What seems toxic and lethal from one perspective becomes nourishing from another. The same chemicals that would kill many surface organisms become the foundation of entire communities here. Context is everything. Poison is just energy wearing the wrong label. By introducing hydrothermal vents, we introduce the idea that ecosystems can be anchored to geology itself. Life does not always need gentle conditions and steady sunlight. Sometimes it thrives best at the edges, where extremes collide and energy leaks out of the planet. And these vents are not exceptions. They are proof that life, when given even the strangest opportunity, will figure out how to turn it into a living. To understand how life survives without sunlight, we have to meet the true culinary pioneers of the deep sea, chemosynthetic bacteria. These microbes have rejected the entire concept of photosynthesis and replaced it with something far stranger. Instead of asking the sun for energy, they turn to chemistry, specifically the kind that would make most surface animals wrinkle their noses and back away slowly. At the heart of chemosynthesis is a simple but radical idea. Energy does not have to come from light. It can come from chemical reactions. Certain compounds contain stored energy, and if an organism can unlock it, That energy can be used to build sugars, repair cells, and grow. Or where plants use sunlight to power this process, chemosynthetic bacteria use chemicals like hydrogen sulfide, methane, or hydrogen gas. Hydrogen sulfide is a favorite in many deep-sea environments. To us, it smells like rotten eggs and broken promises. To chemosynthetic bacteria, it smells like breakfast. These microbes oxidize hydrogen sulfide, stripping electrons from it in controlled chemical reactions. The released energy is captured and used to convert carbon dioxide into organic molecules. This is food production without farming, cooking, or photosynthesis. Just chemistry doing its thing. What makes this process so impressive is its efficiency under extreme conditions. These bacteria operate in crushing pressure, near freezing temperatures, and complete darkness. None of that matters to chemistry. As long as the right molecules are present, reactions proceed. Life simply rides along. Unlike photosynthesis, which depends on a steady supply of sunlight, chemosynthesis depends on chemical availability. This means the bacteria must live where these compounds are consistently produced. They do not wander aimlessly. They position themselves precisely where chemical gradients are strongest, balancing access to energy with survivable conditions. Too much hydrogen sulfide can be deadly. Too little, and there is nothing to eat. This balancing act has shaped bacteria into master chemists. They regulate their internal chemistry with extreme precision, preventing toxic buildup while extracting every possible bit of usable energy. It is like eating poison for breakfast, lunch, and dinner, but only after carefully measuring the dose and pairing it with just enough oxygen to avoid disaster. The energy harvested through chemosynthesis is then converted into biomass. Carbon dioxide, usually treated as waste by animals, becomes raw material. Bacteria stitch carbon atoms together into sugars, proteins, and fats, forming the physical substance of living cells. In doing so, they turn invisible chemistry into something tangible, something edible. From an ecosystem perspective, this is the critical moment. Chemosynthetic bacteria transform raw chemical energy into biological matter. They become food, shelter, and infrastructure all at once. Without them, chemically powered ecosystems simply would not exist. They are not a supporting cast. They are the opening act, the main course, and the reason the restaurant is open. While there is also an elegance to chemosynthesis that often goes unnoticed, it does not require seasons, daylight cycles, or weather. It runs continuously, day and night, year after year, as long as the chemistry holds. This makes it remarkably stable in environments where sunlight would be useless even if it could reach them. The humour in calling this fine dining is not entirely misplaced. From a biochemical standpoint, chemosynthesis is sophisticated. It involves complex enzyme systems, precise molecular choreography, and exquisite control over reaction rates. These bacteria are not sloppily burning chemicals. They are carefully preparing an energy-rich meal from ingredients most life would consider lethal. What is perhaps most humbling is that this process does not care about complexity or intelligence. It works just as well for single-celled organisms as it does as the foundation for entire ecosystems. Chemosynthesis proves that you do not need leaves, roots, or sunlight to feed the world. You need chemistry and a willingness to embrace truly questionable flavors. In the deep sea, rotten egg smell is not a warning. It is an invitation. And chemosynthetic bacteria accept it every time, turning toxic molecules into the fuel that powers life in total darkness. Once bacteria figure out how to turn raw chemistry into usable energy, everything else in the ecosystem lines up behind them like shoppers outside a bakery. These microbes are not background characters. They are the foundation, the infrastructure, and the food supply all at once. In deep-sea ecosystems, built without light, bacteria do the job that forests, grasslands, and plankton do at the surface, except they do it invisibly and without any appreciation. On land, ecosystems begin with plants. In the deep sea, they begin with bacteria. These microbes form thick mats across rocks, sediments, and vent structures, coating the seafloor like living carpets. At first glance, these mats look unimpressive, like pale fuzz or slimy paint. But functionally, they are biological factories running non-stop. Every cell is busy converting chemical energy into organic matter, building the base that everything else depends on. What makes this role so important is that nothing larger than a microbe can tap directly into the raw chemical energy pouring out of the seafloor. Animals cannot just sip toxic fluids and call it lunch. They need food that is already packaged into molecules they can digest. Bacteria do that packaging. They take invisible chemical reactions and turn them into biomass. In ecosystem terms, they are the entry point where energy becomes edible. Because of this, bacterial growth rates in these environments can be astonishing. Where chemical energy is abundant, microbial populations explode, producing dense concentrations of organic material in places that would otherwise be nearly lifeless. Compared to the surrounding deep sea, which often operates on a starvation economy, these bacterial zones are overflowing pantries. It is no wonder larger organisms flock to them. Some animals graze directly on bacterial mats, scraping them off surfaces like underwater lawn mowers. Others rely on bacteria more indirectly, feeding on organisms that already ate the microbes. Either way, the energy trail always leads back to bacteria. Remove them, and the entire structure collapses. No mats, no food, no community. The deep sea does not forgive missing foundations. These microbes also shape the physical environment. As bacterial mats grow, they trap particles, stabilize sediments, and alter the chemistry of the immediate surroundings. They can change how metals precipitate, how fluids move, and even how surfaces feel to other organisms trying to settle there. In this way, bacteria are not just food producers. They are habitat engineers, quietly remodeling the seafloor to suit themselves, and, accidentally, everyone else. One of the most fascinating aspects of these bacteria is how flexible they are. Different species specialize in different chemical niches, and allowing multiple bacterial communities to coexist side by side. Where one chemical dominates, one group flourishes. Where conditions shift slightly, another takes over. This creates a mosaic of microbial zones, each feeding different parts of the ecosystem. It is less like a single field and more like a patchwork farm where every plot grows something different. And unlike plants, which are stuck where they sprout, bacteria can respond quickly to change. If chemical conditions intensify, they grow faster. If conditions weaken, they retreat or shut down. This responsiveness gives deep-sea ecosystems a surprising degree of resilience. As long as bacteria can keep producing organic matter, the system can adjust around them. It is also worth appreciating the scale of their impact. Individually, bacteria are microscopic. Collectively, they support animals that can be hundreds or thousands of times larger. Entire communities of worms, clams, crabs, and fish are effectively living off microbial labor. The bacteria do the hard work of energy conversion, and everyone else shows up to collect rent in the form of calories. There is something humbling about this arrangement. The most visually dramatic creatures of the deep sea, the ones that make documentaries and inspire awe, owe their existence to organisms too small to see without a microscope. In the darkness, power does not belong to the biggest or fastest. It belongs to the smallest, busiest, and most chemically talented. In surface ecosystems, plants get the glory. In the deep sea, bacteria run the show without applause. They are the grass beneath every footstep, the trees no one can climb, and the farmers who never take a day off. Without them, the deep sea would return to silence. With them, entire ecosystems rise from chemistry alone, proving that sometimes the most important life forms are the ones quietly holding everything together. If hydrothermal vents are the deep sea's power plants, then giant tube worms are their most baffling tenants. These creatures look like something a science fiction artist would sketch during a very confident lunch break. They can grow over 2 meters long, live packed together in dense clusters, and wave bright red plumes into the water like they are auditioning for an underwater parade. And yet, despite their size and flair, they are missing what most animals would consider essential survival equipment. They have no mouth, they have no stomach, they have no digestive system at all. And by all conventional logic, this should be a deal breaker. Tube worms do not eat in the way animals usually do. They do not hunt, graze, filter, or scavenge. They never chew, swallow, or digest a single bite of food. Instead, they outsource the entire concept of eating to bacteria that live inside their bodies. It is less a partnership and more a permanent roommate situation where one side does all the cooking and the other provides the apartment. Inside the tube, worm is a specialized organ that takes up most of its body. This organ is packed densely with symbiotic bacteria, millions upon millions of them, all working non-stop. The worm's role is not to feed itself directly, but to deliver the right ingredients to its internal bacterial workforce. In return, the bacteria manufacture organic molecules that nourish the worm from the inside out. The bright red plume at the top of the tube worm is not decoration. It is a highly efficient gas exchange structure. That red color comes from a blood pigment that binds multiple substances at once, allowing the worm to transport everything its bacterial partners need. Think of it as a biological delivery service operating under extreme conditions. No menus, no tips, just constant logistics. The worm absorbs chemicals from the surrounding water and delivers them internally, where the bacteria convert them into usable energy. The worm then absorbs the resulting nutrients directly into its tissues. There is no intermediate step, no digestion, no leftovers. No, and it is a closed loop of cooperation that blurs the line between where the worm ends and the bacteria begin. This arrangement allows tube worms to grow at astonishing rates. In an environment where food can be unpredictable, they bypass the usual bottlenecks of feeding and digestion. As long as conditions remain favorable, their internal factories keep running, fueling rapid growth and long lifespans. Some individuals are thought to live for decades, quietly standing like organic skyscrapers on the seafloor. What makes this relationship especially remarkable is how specialized it is. Tube worms cannot survive without their bacteria, and the bacteria cannot survive outside the worm. They are evolutionarily intertwined to the point that neither makes sense alone. This is not a casual partnership. It is a biological merger. The worm's tube itself adds another layer to the story. Made of a tough, chitin-like material, the tube anchors the worm in place and protects its soft body from predators and environmental stress. Once settled, a tube worm is committed. It cannot crawl away if conditions worsen. Its entire survival strategy depends on remaining plugged into the right chemical environment and maintaining its internal bacterial population. And yet, despite being rooted in place, tube worms dominate their habitat. Their sheer size and density reshape the ecosystem around them. They provide surfaces for other organisms to cling to, create shelter from currents and alter how fluids flow across the seafloor. Entire communities grow up around these towering worms, using them as both structure and landmark in the darkness. Yes, there is something deeply ironic about tube worms. They are among the most successful animals in one of the harshest environments on Earth. Yet they achieve this success by giving up the basic act of eating. Instead of competing for food, they turn their bodies into food-producing systems. Instead of hunting, they host. Calling them freeloaders is only half fair. Yes, they let bacteria do the hard work, but in exchange, they provide protection, resources, and a stable environment in a place where stability is rare. It is mutual dependence elevated to an art form. Everyone pays rent. Everyone benefits. Tube worms force us to rethink what it means to be an animal. They challenge the assumption that eating is a defining trait. In their world, survival is not about teeth or speed or cleverness. It is about cooperation at the cellular level, all about building a body that functions as an ecosystem rather than a single organism. In the darkness of the deep sea, giant tube worms stand as living proof that evolution does not care about tradition. If abandoning your mouth lets you thrive, then goodbye, mouth. Life does not follow rules. It follows results. If giant tube worms represent one extreme solution to life without light, vent clams and mussels represent a slightly more familiar one, at least in shape. They look like clams. They behave like clams. They sit there, open and close, and generally mind their own business. And yet, beneath that familiar shell is a strategy that is anything but ordinary. These animals are not just filter feeders waiting for food to drift by. They are farmers. Vent clams and mussels host dense populations of bacteria inside their tissues, and especially within their gills. These gills are massively enlarged compared to their shallow water relatives, not to filter plankton, but to house microbial partners. The animals carefully position themselves where chemical-rich fluids mix with seawater, creating just the right conditions for their internal bacteria to thrive. Location matters. Too close, and the chemistry becomes lethal. Too far, and the energy supply runs dry. These animals have turned real estate selection into a survival skill. Inside their bodies, the bacteria go to work, converting chemical compounds into organic matter. The clam or mussel then absorbs the nutrients produced by these microbes, effectively harvesting food grown within its own tissues. It is farming, but instead of soil and sunlight, the crops are microbes, and the fertilizer is chemical seepage from the Earth's crust. Unlike tube worms, these bivalves still retain the basic anatomy of clams and mussels. They can open and close their shells, control water flow, and regulate how much chemistry reaches their bacterial partners. This gives them a degree of control over their internal ecosystem. Too much chemical input can stress the bacteria. Too little starves them. The animal acts as both landlord and climate control system, fine-tuning conditions to keep its microbial tenants productive. This strategy allows vent clams and mussels to form dense beds on the seafloor, sometimes covering vast areas around vent fields. These beds are among the most visually striking features of deep-sea ecosystems, rows of shells packed together like an underwater market. Where they appear, biomass skyrockets. Life piles up in places where, by all rights, nothing should be able to live. What makes these animals particularly interesting is their flexibility. Some species can still filter feed to a limited extent, supplementing their diet when conditions allow. This dual capability acts like a biological backup plan. If chemical conditions fluctuate, they are not entirely helpless. They can adjust their feeding strategy, at least temporarily. In an environment defined by change, versatility is a powerful advantage. The presence of clam and mussel beds also reshapes the surrounding ecosystem. Their shells provide hard surfaces in an otherwise soft sediment environment, creating attachment points for other organisms. Small animals take shelter between shells. Predators learn to patrol these areas, as drawn by the abundance of potential prey. The bivalves do not just benefit from the ecosystem, they help build it. These animals also influence local chemistry. By absorbing certain compounds and releasing others, they subtly modify the environment around them. Their bacterial partners play a role in this process, altering chemical gradients in ways that can make surrounding areas more or less hospitable. The ecosystem becomes a feedback loop, shaped by the organisms living within it. There is something oddly domestic about this arrangement. While the deep sea is often portrayed as alien and hostile, vent clams and mussels embody a kind of quiet routine. They settle, they maintain, they manage their internal farms day after day in total darkness. No drama, no chasing, just steady biological productivity under extreme conditions. And of course, from a human perspective, the idea of living inside a sulfur-scented greenhouse at crushing pressure does not sound relaxing. But evolution does not optimize for comfort. It optimizes for survival. And in that regard, vent clams and mussels are spectacularly successful. They show that cooperation with microbes is not a one-size-fits-all solution. Different animals adopt different levels of dependence, different degrees of control, and different ways of integrating bacteria into their bodies. Tube worms surrender completely. Clams and mussels negotiate. Both strategies work. By turning their bodies into living farms, these bivalves blur the line between organism and ecosystem. They are not just animals occupying space. They are environments in their own right, hosting communities that make their own survival possible. In the deep sea, even a clam can be a city, quietly growing food in the dark, surrounded by chemistry, and absolutely unconcerned with the absence of sunlight. Once the foundation is in place and primary production is handled, something familiar begins to emerge in an otherwise alien world. A food web. Not a neat pyramid, not a tidy diagram you would see in a textbook, but a living, shifting network of who eats whom in a place where the rules were rewritten. At hydrothermal vents, energy does not trickle down gently from leaves and plankton. It radiates outward from chemical hotspots, and everything else arranges itself accordingly. At the edges of bacterial abundance, grazers take center stage. These are animals that feed directly on microbial growth, scraping, rasping, or vacuuming bacteria off surfaces. Snails cruise across mineral chimneys like tiny vacuum cleaners with ambition. Limpet-like creatures cling tightly and graze methodically, turning biofilms into bite-sized meals. Their movement patterns often trace invisible energy gradients, clustering where bacterial productivity is highest, and thinning where chemistry fades. These grazers convert microbial matter into animal tissue, and that is when the food web gets interesting. Because once energy is packaged into something with muscles, predators arrive. Crabs patrol vent fields with deliberate confidence, armed with claws built for cracking shells and grabbing whatever moves slowly enough to be grabbed. Some fish hover just beyond the densest clusters, darting in to snatch prey before retreating to slightly calmer waters. The vents are busy, but not chaotic. Every movement seems calculated, as if wasting energy would be socially unacceptable. Scavengers play an equally important role. In an environment defined by extremes, death is frequent. When organisms die, their bodies do not go to waste. Shrimp, worms, and small crustaceans converge quickly, recycling organic matter back into the system. Nothing lingers long enough to become debris. In this way, vent ecosystems operate with ruthless efficiency. Energy enters through chemistry and is reused as many times as possible before drifting away. What makes this food web so unusual is how compressed it is. On the surface, energy often travels through long chains, from plants to herbivores to multiple levels of predators. At vents, those chains are short and intense. Energy moves quickly from microbes to animals to predators, what with fewer steps in between. This creates ecosystems that are dense, dynamic, and surprisingly productive given their isolation. Another strange feature is how spatially structured everything is. Predators do not roam randomly. They patrol specific zones where prey is abundant. Grazers cluster where bacterial growth is thickest. Scavengers linger on the margins, ready to move in. The entire community is organized around distance from chemical output, like concentric rings around an invisible center. Move a few meters in the wrong direction, and the food web thins dramatically. Competition also plays out differently here. Instead of fighting over sunlight or territory, organisms compete for access to chemistry-shaped habitats. Position matters more than possession. Being in the right spot can mean constant food. Being slightly off means starvation. This leads to dense clustering and surprisingly tolerant behavior, where species live shoulder to shoulder because the alternative is leaving the buffet. Despite the harsh conditions, these food webs are not simplistic. Multiple predators may target the same prey. Grazers may switch feeding surfaces depending on conditions. Scavengers may become opportunistic hunters if the chance arises. Roles blur. Flexibility is rewarded. In a place where conditions can change suddenly, rigid specialization can be a liability. There is also an odd sense of balance. Even though energy flows from a volatile source, the communities often appear stable over long periods. Predator populations do not explode unchecked. Grazers do not strip surfaces bare. Feedback loops emerge naturally, driven by energy availability rather than light cycles or seasons. The system regulates itself through chemistry and consumption. Watching a vent food web in action feels like watching an alien version of a familiar story. The characters are strange. The setting is extreme, but the plot is recognizable. Life organizes itself around available energy. It creates producers, consumers, and recyclers. It builds networks of dependence and competition. It fills niches, whether the source of energy is a star or a crack in the earth. In the end, vent food webs remind us that ecology is not about sunlight. It is about flow. Energy enters, moves, transforms, and eventually dissipates. At hydrothermal vents, that flow begins in darkness, surges outward through chemistry, and supports entire communities that spin around it faithfully, as like planets orbiting a star that burns without light and smells faintly of sulfur. To appreciate just how unusual vent ecosystems are, it helps to understand how slow life usually is in the deep sea. Away from chemical hotspots, the deep ocean operates on patience. Growth is measured in years. Reproduction is cautious. Many animals live long lives doing very little. Conserving energy like it is a dwindling savings account. Food arrives sporadically, often as falling debris from far above. And when it does, everything waits its turn. It is an environment where rushing rarely pays off. Hydrothermal vent communities flip that script entirely. At vents, energy is not arriving in crumbs. It is flowing continuously. As long as the vent remains active, chemical compounds pour into the surrounding water without pause. And this steady supply creates conditions that allow biological production to run at full speed. There is no long wait between meals, no seasonal famine, no guessing when the next delivery will arrive. For deep sea life, this is about as close as it gets to a reliable meal plan. Because energy input is constant, microbial growth can proceed rapidly. Dense bacterial populations generate organic matter at rates that dwarf what is typical for the surrounding seafloor. That productivity cascades upward. Grazers find more food, predators find more prey, and populations can expand quickly. The result is an ecosystem that feels almost frantic compared to the rest of the deep ocean, buzzing with activity in a place usually defined by stillness. Rapid growth also changes life history strategies. In much of the deep sea, organisms grow slowly and reproduce infrequently because energy is limited. At vents, many species grow fast and reproduce early. There is an urgency baked into their biology. Vents are productive, but they are not permanent. Geological activity can shut them down without warning. Evolution has responded by favoring species that can take advantage of good conditions immediately. This is why vent communities often appear suddenly and expand rapidly once conditions are right. Larvae arriving at an active site do not ease into things. They settle, grow, and reproduce as quickly as possible. The ecosystem does not creep into existence, it bursts into it. The physical environment also supports fast growth. Warm temperatures near vents speed up biochemical reactions, allowing organisms to process energy more quickly. And combine warmth with abundant chemical fuel, and metabolism can run at high gear. It is the biological equivalent of turning up both the thermostat and the grocery budget. Another factor is efficiency. Energy pathways at vents are short and direct. There are fewer steps between primary production and higher consumers, which reduces energy loss along the way. Less energy wasted means more energy available for growth. In ecological terms, vents are streamlined systems with minimal overhead. This productivity creates striking contrasts. A few meters can separate a thriving vent community from an almost barren seafloor. Step out of the energy flow, and growth rates plummet. Step back in, and life surges. It is like walking from a desert into a city overnight, except the city is built of worms, clams, and bacteria, and nobody has ever seen the sun. Fast growth also encourages dense clustering. Organisms pack tightly together to stay within optimal conditions. This proximity further enhances productivity by retaining heat, trapping chemicals, and stabilizing microhabitats. The community becomes self-reinforcing, growing not just because energy is abundant, but because life itself helps maintain the conditions it needs. Of course, this speed comes with risks. When vents shut down, ecosystems can collapse just as quickly as they formed. Populations dependent on constant energy input face sudden starvation. This boom and bust dynamic is rare in the deep sea, where change is usually glacial. Vents introduce a tempo more reminiscent of surface ecosystems, but compressed into an environment that otherwise runs on geological time. That is why vents feel like anomalies. They are pockets of urgency in a world of waiting, places where life does not slow down, even under immense pressure and eternal darkness. They are the deep sea's version of fast food, except the menu is chemistry, and the customers evolve to survive it. In the end, the rapid growth of vent ecosystems is not a mystery. It is a consequence of steady energy, efficient transfer, and evolutionary strategies shaped by instability. Give life a constant fuel source in the deep sea, and it does not hesitate. It grows, it multiplies, and it takes full advantage of the rare luxury of knowing where its next meal is coming from. If hydrothermal vents are dramatic, loud, and intense, cold seeps are their quieter, more patient relatives. They do not blast superheated fluids into the ocean. They do not build towering chimneys or announce themselves with clouds of mineral-rich plumes. Instead, cold seeps leak. Slowly, constantly, almost politely. And yet, despite their low-key behavior, they support ecosystems just as strange and just as important. Cold seeps form in places where hydrocarbons like methane and other reduced compounds migrate upward through the seafloor. These substances seep out of sediments at near ambient temperatures, which is why they are called cold. Nothing about them feels cold to the organisms that rely on them, though. To life adapted to the deep sea, these leaks are energy fountains disguised as geological afterthoughts. The key difference is pace. Cold seeps operate on geological patience. They can persist for thousands, sometimes tens of thousands of years. Instead of sudden bursts of productivity, they offer a slow, steady release of chemical energy. Think of them less as geysers and more as leaky pipes that never quite get fixed. Annoying for plumbing, fantastic for biology. The chemicals emerging from cold seeps would be considered pollution at the surface. Methane is a greenhouse gas. Oil is an environmental disaster waiting to happen. But in the deep sea, these compounds become currency. Bacteria colonize seep sediments and use these substances as energy sources, transforming what looks like a toxic mess into the foundation of entire ecosystems. It is recycling on a planetary scale, performed by microbes that never asked for applause. Unlike vents, cold seeps often create sprawling habitats rather than tight clusters. Thick microbial mats spread across the seafloor like pale blankets, sometimes stretching for hundreds of meters. These mats alter sediment chemistry, oxygen levels, and nutrient availability, reshaping the environment in slow motion. The seep does not shout, it reshapes. The animals that associate with cold seeps reflect this slower tempo. Communities develop gradually, layering species over time. The environment is more stable, which allows long-lived organisms to settle in and stay put. Instead of racing to exploit a fleeting opportunity, seep inhabitants invest in endurance. This is not a pop-up ecosystem. It is a long-term lease. Cold seeps also appear in a wider range of geological settings than vents. They occur along continental margins, subduction zones, and areas where buried organic material breaks down deep below the surface. This means they are more widespread and more common than hydrothermal vents, even if they are less visually dramatic. They are the deep sea's background infrastructure, quietly supporting life over vast areas. One of the strangest features of cold seeps is how familiar and unfamiliar they feel at the same time. You might find sediments that look muddy and unremarkable, yet they are alive with chemical activity. Beneath the surface, microbial processes are reshaping the environment, locking carbon into minerals, altering the chemistry of seawater, and feeding higher life forms. It is an ecosystem that hides its productivity just below the surface, literally and figuratively. Because cold seeps last so long, they can accumulate thick biological layers over time. Shell beds, carbonate structures, and hardened sediments build up gradually, preserving the history of seep activity, like tree rings in rock. These formations become habitats themselves, creating complexity in an environment that would otherwise be flat and monotonous. The seep writes its biography directly into the seafloor, What makes cold seeps especially fascinating is their role in Earth's larger systems. By hosting bacteria that consume methane, these ecosystems act as biological filters, preventing massive amounts of this gas from reaching the ocean and atmosphere. In other words, these quiet deep-sea communities are quietly stabilizing the planet's climate without ever knowing what a climate is. From a storytelling perspective, cold seeps are easy to underestimate. They lack the spectacle of vents. They do not glow, roar, or erupt. But biologically, they are just as revolutionary. They prove that life does not need intensity to flourish. Given time, chemistry, and stability, ecosystems will assemble themselves patiently, one microbe at a time. Cold seeps remind us that the deep sea is not defined by uniform darkness and scarcity. It is a patchwork of opportunities, some loud, some subtle, some flash into existence, others persist quietly for ages, and in these slow, leaking corners of the planet, bacteria once again demonstrate an astonishing talent for turning what looks like pollution into lunch, and in doing so, building entire worlds beneath our feet. Methane has a reputation problem. At the surface, it is framed as a troublemaker, a gas that traps heat and complicates climate conversations. In the deep sea, however, methane gets a dramatic rebrand. Down here, it is not an environmental villain. It is breakfast and lunch, and the reason entire ecosystems exist where nothing else should. At cold seeps, methane rises slowly through sediments, creating zones where this gas becomes concentrated just beneath the sea floor. This is where methane-eating microbes move in. These microorganisms do something extraordinary. They use methane as an energy source, converting it into organic matter that can support life far beyond their own microscopic bodies. In doing so, they turn an invisible gas into solid food. These microbes do not operate alone. They often form partnerships between different types of microorganisms, working together in tightly coordinated systems. One group activates the methane, another completes the energy extraction, and together they power the production of biomass. The result is thick microbial mats that coat the seafloor, sometimes forming carpets so dense they ripple in the currents, like living fabric. These mats are not just food, they are habitats. They change the chemistry of the surrounding environment, consuming oxygen, producing byproducts, and creating gradients that other organisms learn to exploit. To the untrained eye, a methane seep might look like an empty stretch of sediment. To the organisms that live there, it is a thriving neighborhood built on gas. Animals quickly take advantage of this abundance. Some species feed directly on the microbial mats, grazing across them in slow, deliberate movements. Others rely on organisms that have already converted microbial matter into animal tissue. Either way, methane becomes the starting point of the food web, even though it never exists as something you can bite. One of the most fascinating outcomes of methane-fueled ecosystems is how they blur the line between geology and biology. Methane seeps are geological features, but the life they support actively reshapes them. As microbes consume methane, they trigger chemical reactions that cause minerals to precipitate and harden. Over time, this can create rocky structures in places that were once soft sediment, turning biology into architecture. These hardened formations then become new habitats, providing surfaces for attachment and shelter for animals. The ecosystem builds upon itself, layer by layer, starting with invisible gas and ending with complex communities anchored to stone. It is hard not to admire the efficiency. Nothing is wasted. Everything becomes something else. The productivity of methane-eating microbes also has broader consequences. By consuming methane before it escapes into the ocean, these organisms act as biological gatekeepers, They regulate how much methane moves upward, influencing larger chemical cycles in the ocean. Entire deep-sea communities, unseen and uncelebrated, are quietly moderating processes that affect the entire planet. What makes this especially remarkable is that these microbes thrive in conditions that would shut down most life. Low oxygen, high pressure, and chemical stress are not obstacles. They are prerequisites. Evolution has shaped these organisms to operate where others cannot, turning extreme environments into exclusive opportunities. From an ecological perspective, methane-based communities challenge our intuition about what counts as food. There is no leaf, or no carcass, no particle drifting down from above. Energy arrives as a gas, invisible and intangible, and leaves as living tissue. It is a reminder that food webs do not require familiar ingredients. They require transformation. The thick mats formed by methane-eating microbes are also surprisingly dynamic. They expand, contract, and shift over time as seep activity changes. Animals track these changes, following the energy like shoppers following a sale. The ecosystem breathes, growing where methane flows and fading where it slows, all without ever seeing the sun. In the end, methane-eating microbes embody the deep sea's talent for flipping narratives. What is harmful in one context becomes essential in another. A greenhouse gas becomes the foundation of life. A leak becomes a lifeline. And in the darkness beneath the ocean, methane finds a wholesome second career, not as a problem to be solved, but as the reason entire communities are alive at all. Cold seeps may look calm compared to the chaos of hydrothermal vents, but the conditions they create are anything but gentle. Oxygen is often scarce. Chemicals seep constantly from the sediment, and the environment can shift subtly over time in ways that punish the unprepared. The animals that thrive here are not just tolerant of hardship. They are specialists, fine-tuned by evolution to operate where most life would tap out immediately. Crabs are often among the most visible residents of cold seeps. These are not casual wanderers passing through. They are permanent locals, equipped with adaptations that let them handle low oxygen conditions without panicking. Their metabolism can slow dramatically, conserving energy when conditions worsen. This ability to downshift is crucial in an environment where oxygen levels can fluctuate unpredictably. Think of them as deep-sea hybrids, switching between performance and efficiency mode as needed. Many seep crabs also display behavioral adaptations that maximize survival. They position themselves strategically around microbial mats and chemically active sediments, balancing access to food with avoidance of the most toxic zones. Their movements are deliberate, not rushed. Energy is abundant here, but only if you do not waste it. These crabs are not lazy, they are efficient. Worms take adaptation even further. Cold seep sediments are often dominated by burrowing species that live partially or entirely beneath the surface. These worms interact directly with chemically rich layers, pushing their bodies into environments loaded with compounds that would kill most animals. Their tissues and internal systems are adapted to handle these conditions, either by detoxifying harmful substances or by keeping them isolated from sensitive processes. Some worms act as living mixers, constantly moving sediment and circulating chemicals. This behavior does more than keep them fed. It reshapes the seep environment itself, redistributing nutrients and creating microhabitats that other organisms can exploit. In this way, worms are not just inhabitants. They are ecosystem engineers, quietly remodeling the neighborhood from below. Fish at cold seeps tend to be more elusive, but no less specialized. They often hover at the edges of seep zones, where oxygen levels are slightly higher but food is still plentiful. And their bodies are adapted for low oxygen efficiency, extracting more from each breath than their surface relatives ever need to. Some species also show reduced activity levels, conserving energy and avoiding unnecessary exposure to harsh conditions. What unites these animals is their tolerance for chemistry that would be lethal elsewhere. Compounds that interfere with cellular processes are simply part of daily life here. Over evolutionary time, these species have developed biochemical pathways that neutralize or manage these substances. Survival is not about avoiding toxins. It is about learning to live with them. Cold seep animals also tend to have longer lifespans and slower life histories compared to vent species. The relative stability of seeps allows for this strategy. Instead of racing to reproduce, many seep inhabitants invest in longevity, growing steadily and reproducing over extended periods. It is a different response to a different kind of extreme. Another notable feature is how densely packed these communities can be. Despite harsh conditions, seep ecosystems support high biomass. Animals cluster around productive areas, creating bustling neighborhoods in places that, from afar, look empty and lifeless. The contrast is striking. A few steps away from a seep, the seafloor can be nearly barren. Step into it, and life crowds in. Interactions between species at seeps are shaped by chemistry as much as by biology. Predation, competition, and cooperation all occur within tight environmental constraints. Species must not only interact with each other, but constantly negotiate with their surroundings. The environment is an active participant in every interaction. In many ways, cold seep animals represent the extreme end of adaptation. They are not generalists. They are not flexible wanderers. They are specialists, honed for a narrow set of conditions. And within those conditions, they excel. Outside of them, they struggle. This makes seeps both refuges and traps, places of abundance surrounded by inhospitable terrain. Calling these animals survival experts is not exaggeration. They endure low oxygen, toxic chemistry, and isolation, all while maintaining functional ecosystems in total darkness. They are living proof that life does not need comfort to thrive. It needs opportunity, adaptation, and time. In the deep sea's harshest neighborhoods, cold seep animals have mastered all three. By now, and it should be clear that not all deep sea ecosystems without light are built the same. Hydrothermal vents and cold seeps may both run on chemistry instead of sunlight, but the similarities mostly end there. When you zoom out and look at the bigger picture, these systems resemble two cities powered by entirely different fuels, each shaping its skyline, culture, and pace of life in unique ways. Hydrothermal vent ecosystems are defined by intensity. Their energy source arrives hot, fast, and often violently. This shapes everything about how life organizes itself there. Biological communities at vents tend to be tightly clustered, packed close to the source of chemical output. Space is limited, competition is fierce, and growth is rapid. The architecture of vent ecosystems is vertical and crowded, with organisms stacking, overlapping, and clinging to every available surface. Cold seep ecosystems, in contrast, are defined by persistence. Their energy source arrives slowly and steadily, seeping upward through sediments over long periods of time. This encourages horizontal expansion rather than vertical clustering. Instead of dense towers of life, seeps often support broad fields of organisms spread across the seafloor. The biological architecture is flatter, more expansive, and layered over time. These differences in energy delivery ripple through every level of organization. At vents, species are often adapted for rapid growth and early reproduction, taking advantage of conditions that may not last. At seeps, species tend to favor endurance, investing in long lifespans and slow but steady growth. One ecosystem runs like a sprint, the other runs like a marathon. And the physical structures associated with each system also reflect their energy sources. Vents build mineral chimneys and towering formations as hot fluids cool and precipitate solids. These structures create complex three-dimensional habitats that organisms exploit in creative ways. Seeps, on the other hand, gradually harden sediments and form low-relief carbonate features. Their habitats emerge quietly, shaped as much by biology as by geology. Community dynamics differ as well. Vent ecosystems often experience rapid turnover. Species arrive, flourish, and disappear as conditions change. Cold seep communities evolve more slowly, with stable populations persisting over long timescales. This stability allows for more intricate interactions and long-term relationships between species. Even the way organisms move reflects these differences. Vent species often display behaviors that keep them close to energy sources, minimizing unnecessary travel. Seep species may range more widely across productive sediments, spreading out rather than clustering tightly. Both strategies are effective, but they are responses to fundamentally different energy landscapes. Despite these contrasts, both systems reveal the same underlying principle. The nature of the energy source shapes the ecosystem built upon it. Change the fuel, and the city redesigns itself. The deep sea demonstrates this principle with remarkable clarity, free from the confounding influence of sunlight. There is also an important lesson in coexistence. Vent and seep ecosystems can occur relatively close to each other, yet remain distinct. Species adapted to one rarely thrive in the other. And this separation reinforces how specialized these systems are. Chemistry is not just an energy source. It is a filter that selects for certain life strategies while excluding others. Seen together, vents and seeps expand our understanding of what ecosystems can look like. They show that complexity does not require uniformity. Different chemical pathways give rise to different biological forms, each valid, each successful within its context. There is no single blueprint for life without light. In the end, comparing vents and seeps is like comparing two cities powered by strange technologies. One runs on explosive geothermal output, glowing with urgency. The other hums quietly on leaking hydrocarbons, patient and persistent. Both are alive. Both are thriving. And both exist because life figured out how to turn weird science into a home. Time behaves differently in the deep sea, and nowhere is that more obvious than in ecosystems built on chemistry instead of sunlight. On the surface, we are used to ecosystems that feel permanent. Forests grow over centuries. Reefs take millennia to build. Even when disasters strike, the expectation is eventual recovery. In the deep sea, permanence is optional. Some ecosystems live fast and vanish young. Others linger so long they feel practically eternal. Hydrothermal vents sit firmly in the first category. They are born from geological activity, and geology is not sentimental. A vent exists only as long as pathways beneath the seafloor remain open and active. When those pathways clog, shift, or cool, the vent shuts down, sometimes gradually, sometimes abruptly. A once roaring source of energy can fall silent in a geological blink. From a biological perspective, this makes vents unreliable landlords. Communities may flourish for decades, only to face sudden collapse when the chemical supply disappears. The structures remain, but the energy is gone. For organisms dependent on constant chemical input, this is catastrophic. Entire ecosystems can fade within years, leaving behind empty shells and mineral skeletons as quiet evidence that life was once there. This impermanence shapes everything about vent communities. Species that thrive there are adapted to urgency. They grow quickly, reproduce early, and disperse widely. Evolution has favored those that treat vents not as forever homes, but as temporary opportunities. Live hard, reproduce fast, be ready to leave. Cold seeps, by contrast, feel almost timeless. And their energy sources come from deeply buried processes that unfold slowly. Methane and other hydrocarbons can seep upward for thousands of years, sometimes longer. From the perspective of an animal, a cold seep may as well be permanent. Generations come and go without the energy supply ever shutting off. This stability allows seep communities to mature in ways vent communities rarely do. Populations grow old together. Long-lived species settle in and invest in the environment. Physical structures accumulate. The ecosystem develops history, where vents feel like pop-up shops that appear overnight and disappear just as quickly. Seeps feel like ancient villages built layer by layer. The contrast creates two very different ecological personalities. Vent ecosystems are dynamic and restless. Seep ecosystems are patient and enduring. Both are successful, but they succeed on different timescales. One thrives on speed, the other thrives on persistence. These differences also affect how communities respond to disturbance. When a vent shuts down, there is little chance of recovery at that exact location. Life moves on, searching for the next opportunity. At seeps, disturbances may be absorbed and healed over time. The system bends rather than breaks. Interestingly, the deep sea contains records of these timelines written directly into the landscape. Abandoned vent structures mark places where ecosystems once pulsed with life. Hardened seep formations record thousands of years of slow biological activity. The seafloor is a history book, written in chemistry and stone, if you know how to read it. For the organisms living there, as time is not measured in calendars but in conditions. As long as energy flows, life continues. When it stops, life adapts, migrates, or disappears. There is no nostalgia, no clinging to lost habitats, just constant adjustment to what is available now. This temporal diversity adds resilience to the deep sea as a whole. Because ecosystems operate on different timescales, the loss of one does not mean the loss of all. Some communities blink out, while others endure. Over geological time, this patchwork of lifespans creates a dynamic but persistent biosphere beneath the waves. From our perspective, it is tempting to assign value based on longevity. Ancient villages feel more important than pop-up shops. But in the deep sea, both matter. Short-lived vent ecosystems drive rapid evolution and dispersal. Their long-lived seep ecosystems provide stability and continuity. Together, they form a system that can survive change precisely because it does not rely on permanence. In the end, the lifespan of these ecosystems teaches a quiet lesson. Life does not need forever. Sometimes it needs only a window. Sometimes it needs patience, measured in millennia. And in the darkness of the deep sea, both strategies work beautifully, building worlds that last just long enough to matter. In a world without light, seeing is optional. Sensing is not. For animals living in deep sea ecosystems built without sunlight, survival depends on interpreting a constant stream of chemical information drifting through the water. Where surface animals rely on sight to navigate, hunt, and socialize, deep-sea animals rely on chemistry. Smell, in its many specialized forms, and becomes the primary way of understanding the world. Chemical cues in the deep sea act like invisible signposts. They indicate where energy is available, where danger may lurk, and where potential mates might be found. These cues spread through water as gradients, becoming stronger closer to their source. Animals have evolved to detect incredibly faint differences in concentration, allowing them to orient themselves in total darkness with surprising precision. This chemical awareness begins at the sensory level. Many deep-sea animals possess highly sensitive receptors tuned to specific compounds associated with food or biological activity. These receptors are often distributed across antennae, tentacles, or other protruding body parts, increasing the surface area available for detection. The animal does not need to see its environment, but it reads it, molecule by molecule. Following a chemical trail is not as simple as moving toward a stronger smell. Deep sea currents twist and distort chemical plumes, breaking them into patches and filaments. Animals must interpret this patchy information, adjusting their movement constantly to stay within the signal. It is less like following a straight road, and more like navigating a scent-based obstacle course in slow motion. This sensory strategy influences behavior in subtle but profound ways. Movements tend to be deliberate and efficient. Sudden bursts of speed are rare unless absolutely necessary. Energy is conserved, and every action is informed by chemical feedback. The result is a style of movement that appears calm and controlled, even when the animal is actively searching. As chemical sensing also plays a central role in reproduction. In the absence of visual signals, many species release chemical cues that announce their presence and readiness to mate. These signals can travel surprising distances, guiding potential partners through the darkness. Timing becomes critical. Releasing signals when conditions are favorable increases the chances that they will be detected rather than diluted or swept away. Some species synchronize their reproductive cycles based on environmental chemistry, ensuring that signals are released when others are most likely to respond. In this way, chemistry replaces courtship displays, colors, and dances. Romance in the deep sea is invisible, but it is not subtle. The reliance on chemical cues also affects how animals avoid danger. Sudden changes in water chemistry can signal disturbances, predation, or harmful conditions. Animals respond quickly, retreating or altering behavior long before any physical threat becomes apparent. Chemistry provides early warning in a place where visual alarms are impossible. One of the most remarkable aspects of chemical sensing is its specificity. Animals do not just detect general smells. They distinguish between different compounds, concentrations, and combinations. This allows them to identify not just food, but the right kind of food, or the presence of specific species. The deep sea may be dark, but it is information-rich for those equipped to read it. This chemical worldview reshapes how animals interact with their environment. Surfaces are not just physical structures. They are chemical landscapes coated in signals. Water is not empty space. It is a medium filled with messages. Every movement leaves a trace, and every trace has meaning. From our perspective, it is tempting to think of smell as a lesser sense, something vague and imprecise. In the deep sea, it is neither. It is the dominant sensory language, refined by evolution, to operate with extraordinary accuracy. It allows animals to build mental maps of their surroundings without ever seeing them. Turning smell into vision may sound like a downgrade, but in the deep sea, it is an upgrade. Light cannot reach these depths. Chemistry can. And so life adapted, trading sunsets and silhouettes for gradients and plumes. The result is a world navigated not by eyes but by noses sensitive enough to see in the dark, even if everything smells faintly like sulfur. Or when you look at deep-sea ecosystems powered by chemistry instead of sunlight, it is tempting to think of them as strange exceptions. Clever hacks life invented later on. But there is another possibility, one that quietly flips the story of life on Earth upside down. These ecosystems may not be odd innovations at all. They may be echoes, living reminders of how life got started in the first place. Early Earth was not a friendly place. There were no forests, no oxygen-rich skies, no gentle food chains stretching toward the sun. The planet was hotter, more geologically active, and chemically chaotic. Volcanoes were common. The crust was restless. The atmosphere lacked the breathable oxygen we take for granted today. Sunlight was present, but the biological machinery needed to harness it efficiently did not yet exist. Life, if it was going to emerge at all, needed another way to get started. This is where chemically powered ecosystems become historically important. Long before photosynthesis transformed the planet, Earth was already producing energy-rich chemical gradients through its own internal processes. Water interacted with hot rock. Minerals dissolved and reacted. Chemical compounds accumulated and moved. These conditions created natural energy flows, exactly the kind life needs to get off the ground. Deep-sea environments today offer a glimpse of what that ancient world might have been like. They show how chemistry alone can support complex biological systems without any reliance on sunlight. In doing so, they provide a plausible framework for how early life could have survived and evolved before green plants ever entered the scene. One of the key challenges for early life would have been consistency. Random chemical reactions are not enough. Life requires steady energy sources that persist long enough for complexity to build. Geological processes provide exactly that. Unlike sunlight, which depends on planetary orientation and atmospheric conditions, Earth's internal chemistry operates continuously. As long as the planet remains geologically active, energy flows. In these chemically rich environments, simple organisms would have had access to natural gradients that could be exploited. Differences in chemical concentration, temperature, and mineral availability create opportunities for reactions to occur repeatedly. Over time, systems that could harness these reactions more efficiently would have gained an advantage. This is the basic logic of evolution, applied long before animals or plants existed. What makes this idea especially compelling is that it removes the need for sunlight as a starting point. Instead of life waiting for photosynthesis to appear, life could have emerged first, powered by chemistry, and only later learned how to tap into solar energy. Photosynthesis, in this view, is not the foundation of life. It is an upgrade. This perspective also helps explain why modern chemically powered ecosystems feel so complete. They are not improvisations. They are refinements of ancient strategies that have been working for billions of years. The deep sea is not inventing something new. It is preserving something old. There is a poetic symmetry here. The environments that may have nurtured Earth's earliest life still exist today. Hidden beneath kilometers of water, are quietly operating as they always have. They are time capsules, not frozen in the past, but continuing to evolve while retaining their core principles. Studying these ecosystems allows scientists to test ideas about early life without relying solely on rocks and fossils. Living systems provide clues about what is possible, what is stable, and what kinds of energy flows can support complexity. They show that life does not need gentle conditions to begin. It needs opportunity and persistence. This connection to Earth's history also reframes our relationship with the deep sea. These environments are not just curiosities. They are chapters in the planet's autobiography. They tell a story of how life learned to exist before the world became green and breathable. In that sense, every chemically powered ecosystem is doing double duty, and it supports modern life while also preserving an ancient way of living. Beneath the ocean, life continues to practice strategies that may be older than sunlight-driven ecosystems on land. Long before leaves reached for the sky, before algae colored the oceans, before oxygen reshaped the atmosphere, chemistry ruled, and deep in the darkness today, it still does. Once you accept that life does not need sunlight, the universe suddenly feels a lot more crowded. For most of human history, the search for life beyond Earth focused on finding places that looked familiar. Blue skies, liquid water, a star shining overhead. The logic was simple. If life here depends on sunlight, life elsewhere probably does too. Chemosynthetic ecosystems quietly dismantle that assumption. On Earth, we now know that life can build complex, self-sustaining communities in total darkness, powered entirely by planetary chemistry. This realization has sent scientists looking outward with fresh eyes toward worlds that were once dismissed as frozen, barren, or irrelevant. Some of the most exciting candidates are not planets at all, but moons orbiting giant planets far from the Sun. Europa, a moon of Jupiter, is wrapped in a thick shell of ice, beneath which lies a vast ocean of liquid water. Enceladus, orbiting Saturn, hides a global ocean beneath its icy crust and actively sprays plumes of water and chemicals into space. These worlds receive very little sunlight, certainly not enough to power photosynthesis as we know it. And yet, they show signs of something even more intriguing: internal energy. Tidal forces generated by their parent planets need these moons from the inside, creating heat through friction. That heat interacts with water and rock, driving chemical reactions deep below the ice. In other words, these moons may have the same fundamental ingredients that support chemosynthetic ecosystems on Earth: liquid water, chemical energy, and geological activity. This is where the deep sea becomes a cosmic guidebook. Hydrothermal vents and cold seeps show us that if those ingredients are present, life does not need a star to thrive. It needs gradients. It needs chemistry in motion. It needs time. Europa and Enceladus appear to check all three boxes. The excitement is not just theoretical. Observations of Enceladus have revealed water vapor and organic molecules erupting from fractures in its ice. Europa's surface shows signs of interaction between the ocean below and the ice above. Yet these are not static worlds. They are active, restless, and chemically interesting. To scientists familiar with Earth's deep sea, that combination rings very loud bells. What makes this idea especially powerful is that chemosynthetic life does not need to be rare or fragile. On Earth, it thrives in extreme environments, enduring pressure, toxicity, and darkness. It builds ecosystems, not just isolated microbes. If similar conditions exist elsewhere, there is no reason to assume life would not take advantage of them. Of course, life on these moons would not look like anything we know. There would be no fish, no worms, no clams. But the underlying logic could be the same. Microorganisms harnessing chemical energy, communities forming around energy sources, complexity emerging without sunlight ever playing a role. This shifts how we think about habitable zones. Instead of focusing solely on distance from a star, Scientists now consider internal energy sources. A world far from the sun can still be alive if it has the right chemistry and geology. In some cases, these worlds may even be more stable over long periods than planets exposed to variable stellar output. There is also a philosophical shift at play. Chemosynthetic ecosystems suggest that life is not a fragile accident clinging to narrow conditions. It is adaptable, opportunistic, and surprisingly creative. Given the right ingredients, it finds a way. The deep sea taught us that lesson first. Now it is teaching us to look beyond Earth with greater confidence. When scientists get excited about Europa and Enceladus, they are not chasing science fiction. They are following a blueprint already tested on our own planet. Somewhere beneath layers of ice, in oceans that have never known daylight, chemistry may be quietly assembling living systems. No sunrises, no photosynthesis, just energy, water, and time doing what they have always done when given the chance. If life can thrive in the darkness beneath our oceans, it can do so elsewhere. And suddenly the universe feels a little less lonely. For most of human history, the deep sea was protected by one simple fact: we could not reach it. Distance, pressure, and darkness acted like natural guardians, keeping our influence mostly at the surface. That era is ending. Technology is pushing deeper, faster, and with far less patience than the ecosystems waiting below. And for chemically powered communities, this timing could not be worse. And deep-sea mining is often presented as a solution to surface problems. The seafloor contains rich deposits of metals used in electronics, renewable energy infrastructure, and batteries. From a human perspective, it looks like an untapped resource waiting to be collected. From the perspective of deep-sea ecosystems, it looks like bulldozers rolling through the only neighborhood with food. Many of these mineral-rich areas overlap with chemically active habitats. Disturbing the seafloor does not just remove rock, it disrupts chemical flows that ecosystems depend on. Sediments are stirred up, smothering organisms and clogging delicate interfaces where chemistry and biology meet. Plumes of debris can spread far beyond the mining site, affecting communities that are not even directly targeted. The problem is not just physical destruction. Where chemical systems are finely balanced, alter the flow of compounds, and the entire foundation of the ecosystem can collapse. These systems do not recover quickly. Some may not recover at all within meaningful timescales. When energy pathways are interrupted, life does not simply pause and wait. It disappears. Climate change adds another layer of threat, even at depths far removed from the surface. Changes in ocean temperature and circulation can alter how chemicals move through the deep sea. Subtle shifts in current patterns may affect how larvae disperse or how nutrients spread. Warming waters can change chemical reactions, tipping balances that ecosystems rely on. There is also the issue of methane. As ocean temperatures rise, methane trapped beneath sediments may be released more rapidly. While some deep-sea communities are built around methane, sudden or massive releases could overwhelm biological systems that normally regulate it. What was once a controlled energy source could become destabilizing, with consequences that ripple far beyond a single site. Perhaps the most troubling aspect of human impact is how little we know. Many deep-sea ecosystems have been discovered only recently. Some have been observed only once. We are still naming species, mapping habitats, and trying to understand how these systems function. Destroying them now is like tearing pages out of a book before learning the language it is written in. Unlike surface ecosystems, deep-sea communities do not bounce back easily. Low temperatures, slow growth rates, and limited dispersal opportunities mean recovery can take centuries, if it happens at all. From a human timescale, damage is effectively permanent. We may live with the consequences long after the original decision makers are gone. There is also an ethical dimension that is hard to ignore. These ecosystems exist independently of us. They do not provide obvious services like fisheries or tourism. Their value is not transactional. And yet, they represent unique expressions of life, solutions to survival that have taken millions of years to evolve. Erasing them for short-term gain raises uncomfortable questions about responsibility and restraint. The deep sea has always been out of sight, and that has made it easy to overlook. But invisibility is not the same as insignificance. These ecosystems play roles in global chemical cycles, influence ocean chemistry, and hold clues about life's adaptability. Losing them means losing knowledge we cannot replace. What makes this moment especially critical is how fast decisions are being made. Industrial interest is moving more quickly than scientific understanding. By the time we fully grasp how these systems work, some may already be gone. The phrase, "before we even finish learning their names," is not poetic exaggeration. It is a realistic timeline. The deep sea does not protest. It does not make noise. It does not look damaged from the surface. Its silence makes it easy to assume resilience. But chemically powered ecosystems are not invincible. They are precise, balanced, and vulnerable in ways that are easy to disrupt and hard to repair. If the deep sea teaches us anything, it is that life can be astonishingly creative when given time and stability. Human activity threatens to remove both, and then once these hidden worlds are gone, they will not announce their absence. They will simply stop being there, leaving behind a darkness even deeper than before. If there is one lesson the deep sea teaches better than any textbook ever could, it is that life does not care about our expectations. We tend to imagine biology as something that reaches upward, chasing light, blooming under the sun. The deep sea quietly dismantles that idea. Far below the surface, life builds entire worlds without a single photon ever showing up to the party. These ecosystems are not minimal or fragile. They are rich, structured, and surprisingly busy. Energy flows, relationships form, communities grow, compete, adapt, and persist. All of it powered by chemistry, pressure, and patience. It is a reminder that life is not defined by what it uses, but by what it can make use of. For humans, sunlight feels fundamental because it shaped our history. It warms us, feeds our crops, and lights our days. But that perspective is provincial. The deep sea shows that sunlight is just one option among many. Life's true requirement is not light, but opportunity. Where energy gradients exist, life finds a way to climb them. There is something humbling about this. We often frame Earth as a rare oasis, a perfectly balanced world made special by its star. And while that star is important, the deep sea suggests that planetary interiors may be just as powerful. Heat, rock, water, and chemistry can collaborate to build living systems independent of stellar generosity. This realization changes how we see our place in the universe. If life can thrive in the darkest corners of our own planet, then darkness elsewhere no longer feels empty. Icy moons, subterranean oceans, and chemically active worlds suddenly become plausible homes rather than distant curiosities. The universe stops looking hostile and starts looking misunderstood. The deep sea also reframes creativity. We usually reserve that word for art, culture, or intelligence. But life itself is creative. Faced with constraints, it invents solutions. No light? use chemistry, no stability, adapt quickly, no permanence, spread and persist anyway. Evolution is not just survival, it is problem-solving at planetary scale. There is also a quiet joy in knowing that life can be content without the things we cherish most. No sunrises, no blue skies, no green landscapes. And yet these ecosystems are not bleak. They are full of interaction and purpose. Happiness may not be the right word, but functionality and continuity certainly are. Life does not miss the sun if it never needed it. This perspective invites humility in how we think about our own environment. The surface world we dominate is only one expression of Earth's potential. Beneath us lies another, equally valid, equally complex. Ignoring it because it does not resemble us would be a failure of imagination. The deep sea reminds us that the universe is not obligated to mirror our experiences. Life elsewhere, if it exists, may be utterly alien in form and function, yet perfectly at home in its own context. It may thrive in darkness, feeding on chemistry, never knowing what a star looks like. And that is not a limitation. It is a different kind of success. As we finish this journey, whilst the most important takeaway is not a specific fact or mechanism, it is a mindset. Life is adaptable beyond our assumptions. It builds worlds where we expect none. It flourishes where we would not last minutes. And it does so quietly, without asking for attention. Somewhere beneath our oceans, entire ecosystems are carrying on, powered by forces older than forests and deeper than sunlight. Somewhere beyond Earth, similar processes may be unfolding right now, unnoticed and unconcerned with our definitions of habitability. The deep sea does not just expand our understanding of biology, it expands our imagination. And once you accept that life is this creative, it becomes hard to look at the dark places of the universe and see emptiness. More often than not, they are probably full of life that never once thought to look up.